Now see here radioactivity. So we have just seen here the nuclear forces, and and we have discussed about stability and instability of the nucleus in binding energy per nucleon. So we have seen like a heavy nucleus uranium 238 which has got binding energy per nucleon less, they are unstable as compared to the lightweight middleweight nuclei like iron, molybdenum, lanthanum and barium, krypton. Similarly, hydrogen which has got very small value of the binding energy per nucleon, also they combine together to form nuclear to carry out nuclear fusion and the bigger nucleus are formed. So now here when we look at the heavy nucleus like the radium, thorium, maybe uranium also here. So these radioactive nuclei or these materials disintegrate themselves. While disintegration they emit alpha, beta and gamma radiation. So alpha, beta and gamma radiations are emitted by these heavy nucleus. So this phenomenon of the emission of the alpha, beta and gamma radiation by a radioactive material is known as radioactivity, and this was studied by first here H. Becquerel. So he studied about the radioactivity. Now what happens when the alpha particle is emitted by the nucleus? Suppose you have taken a nucleus like this XZA. This is a parent nucleus. When it gives out alpha particle like 2He4, here the alpha particle is considered nucleus of the helium. When it gives out the alpha particle, new element is formed, suppose let it be Y, whose atomic number is reduced by 2 and mass number is reduced by 4. So this is here a daughter nucleus, this is a parent nucleus, and in this process energy is also released, and here this is the alpha emission. So whenever the alpha emission takes place, new nucleus is formed whose atomic number reduces by 2 and mass number reduces by 4. But when we take a beta emission, suppose you have taken ZXA and here it is a minus 1 E0, that is a beta particle, negative electron is known as here the beta particle. Then new element is formed here and this is atomic number increases by 1 and mass number remains same, that is A. But see here nucleus has got only positive charges, then how do we get beta particle, that is a negative. So what happened actually here, the neutron inside the nucleus, that is not a stable one, that breaks into two parts like electron and proton. Because of the production of this positive charge, atomic number increases by 1 and mass number remain same. So this is emission of here, this is called here the beta particle. Now when we take about the gamma emission, suppose you have got ZXA and it is giving out here the gamma like this, this is 0, 0. Gamma is like a photon here which is considered chargeless and massless. So when the gamma emission takes place, new element is formed, that is here, not new element is formed, the same element remain here, that is ZXA here. So what happened actually in gamma emission? See here in gamma emission what happened here, if this nucleus has got a higher energy, then it gives out some energy in the form of the gamma radiation and it becomes stable. So these are the three types of emission, alpha, beta and gamma. So this is about the radioactivity. Now let us discuss laws of radioactivity. Now see here laws of radioactivity. We have already seen here the alpha, beta, gamma emission, they are also considered as laws, but the main law is here the rate of disintegration at any time is directly proportional to the number of atoms present in the sample at that time. So according to the law of radioactivity we can write dN upon dt is proportional to N. N is number of atoms present in sample at any time t. So this is your dN upon dt is proportional to N. So the rate of this dN upon dt is known as rate of disintegration. So rate of disintegration is directly proportional to the number of atoms present in the sample at that time. Now we can write dN upon, here we can write negative sign because the number of atoms are reducing with the time. So we can write dN upon dt is equal to minus lambda n, where lambda is known as radioactive decay constant. So, lambda is known as here radioactive decay constant. So, now we can integrate it. Suppose at t is equal to 0, number of atoms were n is equal to n naught, and at t is equal to t, number of atoms n is equal to n. Then we can integrate it. When we integrate it, we will be getting here dn upon n is equal to minus lambda dt, and when we integrate it, we will be getting dn upon n is equal to minus lambda dt, that is 0 to t, and here we can take n naught to n. So, we can write here its integration is here log e n, here lower limit to upper limit is here, this is minus lambda t 0 to t. This can be written, this can be further solved. So, we can write here log e n minus log e n naught is equal to minus lambda t minus 0, and then we can write log e n upon n naught is equal to minus lambda t. So, we can write n upon n naught is equal to e raised to power minus lambda t. So, n is equal to n naught e raised to power minus lambda t. So, this is the expression for the number of atoms left undecayed at any time t. N is equal to n naught e raised to power minus lambda t. So, we can also represent this thing here with the help of the graph, and we will be getting here like this. If I have taken t here and here is n, it is like this graph is coming. This is here 0 time, here there is n naught, and at the time here suppose we can take here this is n naught by 2, corresponding time will be t half, that is called half life. So, see here, in this case this is the half life here, but before defining the half life we will define radioactive decay constant. So, see here, in the radioactive decay constant we have done n is equal to n naught e raised to power minus lambda t. If I take lambda is equal to 1 upon t, then we will be getting n is equal to n naught e raised to power minus 1, or n is equal to n naught by e. So, here the radioactive decay constant is the reciprocal of the time at the end of which number of atoms left undecayed are 1 upon e times the number of atoms present in the sample initially. So, that can be written actually 1 upon e times n naught is the number of atoms present in the sample initially. So, this is here the definition of the radioactive decay constant. Different materials have got the different radioactive decay constant.